Hello, hello, hello. In this worked example, we're going to be talking about electric cars. Electric cars are this fast emerging technology. Uh, General Motors recently announced that in the next 14 years, they're going to stop selling cars that burn fossil fuels and presumably switch entirely to cars that are electric. So there are lots of important reasons for this switch. Not the least of which is that electric cars, at least at the car, don't emit any carbon dioxide, any greenhouse gases when they're operating. But what I'd like to do in this worked example is to try to analyze the electric car through the energy principle that we've been developing in Physics 107 and see if we can understand some of the basic limitations and challenges that face running a car that runs on batteries. So this picture here shows the basic idea that inside an electric car, there's a battery pack and an electric motor and an electric plug that connects to some electrical source, and electrical energy from the plug is used to store energy inside the batteries. And then you unplug, and then as you drive, the energy, it's a type of potential energy stored in the batteries, are used to drive the electric motor, and the car cruises down the road. So let's dig into what the energy principles has to say about running an electric car. Okay, so here's the situation I want us to think about. There's a car driving down the highway at a flat road, not gaining or losing elevation, just traveling along at a constant velocity v. And so the system that I want to consider is just the car. Let's analyze that. And everything else in this problem are part of the surroundings. So since the car is on level ground, we don't have to worry about the gravitational interaction, but there is air outside the system here. These little dots here are the air molecules. So the car is going to experience a drag force. There's going to be a drag force, which we'll call F drag, and that points, in this case, to the left. And let's write down the energy principle. Says the change in the energy of the system, which just includes the car, is going to be given by the work done by the surroundings on the system. So as the car moves down the road and undergoes a displacement to the right of delta R, uh, there's going to be work done by the drag force, and it's going to be a negative work, of course, because the force points to the left and the displacement is to the right. And so the work is just going to be given, the work done by the surroundings is just going to be equal to the magnitude of the drag force times the magnitude of the displacement, with a minus sign out in front, because as we just argued, the work being done is negative. I'd like to come up with some numbers here and do what we'll call a back of the envelope calculation. Just try to estimate some numbers here. So we've previously argued that the drag force should be proportional to the cross-sectional area of the car times the density of air times the square of the speed. And so the work is that times the magnitude of the displacement, which is basically just how far you've driven the car. And because the work being done is negative, that means that the energy of just what's inside the car has got to decrease over time as you drive a certain distance. And where is that decrease coming? Well, there's a battery inside the car, and energy is stored in the battery. And as you drive, you're depleting that energy, and therefore the energy that is stored in the car is decreasing. So we'll use this formula here to estimate basically how much energy it takes stored in the battery to drive a certain distance. Now, of course, there are other places where the energy is going. There's friction maybe with rubbing the tires on the road, and there's sort of internal friction with the motor parts rubbing against one another. But it turns out drag is a pretty especially if you're driving at high speed, where this v squared term is significant. Drag is an important contribution, and since we're just doing a sort of rough calculation, we get surprisingly good numbers just from this very simple model. So it's a very crude model. So I'm going to put wavy signs in here just to indicate that we're really just doing things very roughly. Let's just say that ballpark, the cross-sectional area of a car is on the order of 1 meter squared. And the density of air we know is 1.2 uh, kilograms per cubic meter, but again, this is such a rough calculation. I'm just going to call that 1 kilogram per cubic meter. And let's pick a speed. So we'll imagine that the car is cruising down the highway at 65 miles an hour, and that turns out to be just nearly 30 meters per second. And we need to square that quantity times delta r, which is just the distance that we're going to drive. And this works out to a drag force of minus 900 newtons times whatever distance we're going to drive. And so if you're going to drive, say, a kilometer, 1,000 meters, it's going to take 900,000 joules of energy to drive 1 kilometer. Right? And that energy, again, is coming from the battery. So you need to store 900,000, nearly a million joules of energy in order for the car to drive a kilometer. And now, of course, nobody wants to drive their car just a kilometer. You want to go a lot further. So, you'd like to be able to go, maybe 300 miles or 500 kilometers to really be able to sell this car on the open market and have people want to drive it. So let's put that number in. Let's call it a million joules per kilometer. That means you need to drive 500 kilometers. That means you need 500 megajoules to drive 500 kilometers, roughly. So the key question is how many batteries, or how big, or how much do the batteries weigh if you're going to give a car this kind of cruising range? If you want to go 500 kilometers and you need 500 megajoules of energy stored in your batteries, what do those batteries look like? So this is a huge question at the center of making electric cars competitive. Here is a chart of progress in battery technology. And the thing that people really focus on is the energy density, how much energy you can get for each kilogram of battery. And the energy units that are being used here are not joules or megajoules. It's more standard to use an energy unit of watt hours. So what's a watt hour? Well, it's makes a lot of sense when you hear the definition. A watt hour is just the amount of energy you would consume if you used energy at a rate of 1 joule per second for 1 hour, or 3,600 seconds. So it's immediately obvious that 1 watt hour is exactly equivalent to 3,600 joules worth of energy. And as you can see, people like Elon Musk, who obviously is extremely focused on building batteries to run electric cars, because that's at the core of Tesla's business. He's tweeting about the progress of this energy density as battery technology is improved, and it's really quite remarkable. Actually, the units of density of watt hours per kilogram are the smaller numbers here, and you can see in 2014 we were at 140 watt hours per kilogram. In 2020, we're all the way up to 350 watt hours per kilogram. And on the horizon is even more improvement. The numbers going up a little bit in terms of watt hours per kilogram, and even more in terms of watt hours per liter. So that means you may not reduce the weight of the batteries all that much in the next 10 years, but you're going to make them pack them into a smaller volume as they improve the way the batteries are constructed. So how much are our batteries going to weigh? Well, 500 megajoules is about 140. Let's write this down. 500 megajoules using this conversion is about 140 kilowatt hours. So that works out to be about 400 kilograms of batteries. That's nearly 900 pounds, which is an awful lot. That's sounding a little bit almost impractical. The good news is it's not quite that bad. The calculation that we did for the drag force, we were a little bit pessimistic here. There's a coefficient out in front. Remember, this was just a rough estimate. It turns out that the drag forces are less than half of what we just calculated here. So it turns out that to get a range of about 300 kilometers with these kinds of batteries really only requires about 200 kilograms worth of batteries. That's still pretty hefty, but it's a little bit more manageable. And the batteries, it's not just the weight that matters, it's how much room they take up. And that's why they're actually concerned not just about the energy density per kilogram, but also the energy density per cubic per volume. Because if you can make the battery smaller, then you have a lot more room in the car to do other things like put luggage. Uh, so so if you had $35,000 today, you could buy a Tesla Model 3, and it has a cruising range of a little bit over what we were using, 350 miles, and you could get from 0 to 60 miles an hour in an astonishing 3.1 seconds. So this is a pretty hot car, and it's expensive, but the prices are coming down dramatically, and people are making less fancy electric cars that are going to be a lot more affordable and a lot more common on the road in just a few years. Just you wait and see. The batteries in the Tesla Model S have something like 82 kilowatt hours of storage, which is about, if you look back at our calculation, that's about what we were assuming. When we cut 140 in half, we got down to 70 kilowatt hours. So this is in the ballpark of the amount of energy that's actually stored in the batteries that come with a Tesla Model 3. So that's it for this worked example. Hope to see you again soon. Bye bye.